So finishing up with a couple quick examples. Um, just here's the math that's going to be involved. So a mass hung from a spring vibrates 15 times in 12 seconds. So 15 times, that means that you had 15 full cycles in 12 seconds. What's the frequency? Well, from the earlier part of the note here, you know it's cycles over time. So you get 15 over 12, and you can convert that to a decimal. You can leave it as a reduced fraction. It's whatever you're most comfortable with. Excuse me. So there we go. There's your frequency. The period, because I know frequency, I know it's just going to be 1 over f. So 1 divided by 1.25, or 12 over 15, ends up being 0.8 seconds. So that means that it takes 0.8 of a second to complete a cycle. And frequency tells me that there's 1.25 cycles in every second. All right. Next example. The frequency of a wave is this. So I know my f. Calculate the period. So period is 1 over f. So 1 divided by 6 times 10 to the 1 hertz. And again, you can leave it in that form. It doesn't really matter. Or you can do the calculation, because I know it kind of freaks people out when they don't get to use their calculator. 0.17 seconds. All right. And the last example on this page. A child on a swing has an amplitude of 1.2 meters. So that's the amplitude. What's the total distance a child moves through horizontally in 3 cycles? So let's just do 1 cycle. And pretty much the only way to do this is by giving yourself a sketch. So you know that child starts in that location. Second one, let's say, gets pulled back. So that means they moved 1.2 back. Stage 3, they move forward. So that means they move forward 1.2. They, excuse me. They then move forward 1.2. Picture 4. In picture 5, they're going to move back 1.2. So to me, it looks like 1 cycle is 4 times 1.2, which gives us 4.8 meters. For 3 cycles, we are looking at 3 multiplied by the 4.8, which will give us 14.4 meters. So therefore, the child will travel a distance of 14.4 meters. Note, if it was displacement, the answer would be 0, because displacement is a vector, and it's how far you are from your original starting point. But because they asked distance, we're actually adding up how far did they travel in that time frame. All right, on to the last set of examples. So, universal wave equation. This is something that is extremely important when it comes to waves and sound. So we know that from kinematics, the velocity of an object in a constant state of motion can be calculated by, and we have our formula, delta D equals v times time. But we want to know the velocity, so we'll just rearrange that equation. V equals delta D over T. So that's just from unit number 1, kinematics. So I'm going to take this down here. We're going to introduce some new terminology. Excuse me. All right. So what is the new terminology? Well, we're no longer looking at distance. We're going to look at a wavelength, how long the wavelength is. So velocity is equal to the length of one wave. So instead of displacement, how far did it travel, we'll talk about how long is one wave. And delta T is the period for one wave. And we can switch that around because we know period is 1 over f. So now if I do some of our math dealing with fractions, we know that it's lambda multiplied by the reciprocal, and we end up with our standard universal wave equation. Now I am going to leave it in the other form as well because there is periods of time, or there's moments when it becomes handy. So there we are. Those are your two equations, and this is your universal wave equation. Please make sure this makes it onto your study sheet because it is extremely important and will be used extensively throughout this unit. So please make sure you do have that labeled clearly. So some examples with that. So calculate the speed of sound leaving a tuning fork. So a tuning fork vibrates, transfers energy, creates sound. We can measure the frequency of the tuning fork, okay, 125 hertz, and the wavelength of one cycle is 275. So from previous equation, we have we have our frequency and we have our length. So it'll be f lambda. The only thing you need to be careful of is that lambda is not in SI, it's in centimeters. So we need to make sure we convert that to 2.75 when you got to work in SI, remember. So we end up with 343.75 meters per second. Okay, so that is the velocity of sound in air. And I'll just put a reminder here. Remember to convert. All right. And final example here. Find the velocity of a wave. So we're looking for velocity. We're given wavelength and we have the period. So using the appropriate formula, we can use this one. So we're looking for velocity. Wavelength is 75 centimeters. We need to use 0.75. And 2 minutes is not SI, so we got to multiply that by 60 in the denominator. So now we're all set to do the calculation. We end up with 6.25 times 10 to the -3 meters per second, so a very slow wavelength, or very slow velocity. So now that allows you to do the homework for this particular the introduction unit. So there's really two things that are going on here. I know there were 3 videos for this and I do apologize. However, you needed the first ones kind of to do the investigation. So it's kind of like doing the first 2 lessons all at once. This is the actual mathematical component. The other one's an investigation using applets that will give you access through the iPads in class, and you can go through that. So probably going to take you a day and a half to go through and cover what's required here. So anyhow, if you have any questions, let me know and we'll get them cleared up.